Chapter 12, Video 1. We are going to be discussing chi-square distributions this chapter. Now, overall, there are three different types of chi-square tests that we're going to do this chapter. Video 1 is going to start off with a goodness of fit test. Video 2 is going to go through a test of homogeneity. And video number 3 is going to go through a chi-square test of association. Now, all three chi-square tests have something in common. They focus on proportions specifically, not means. So I know last chapter we were hypothesizing about means, about one sample, two samples, paired samples. But we are now going to switch gears back to proportions. Though we're not really going to see proportions, but we are going to be talking about counts, which can be converted into proportions out of our total sample size. So what exactly does a chi-square distribution look like? Because we've been dealing with normal distributions and t-distributions, which t-distributions looked a lot like normal distributions, but they were shorter in the middle, fatter on the tails. So what does a chi-square look like exactly? Well, a chi-square is going to look very different from a normal or a t-distribution. Now, some characteristics specifically. All chi-square distributions start at 0. There are no negative chi-square values, so they only take positive values. Now, just like with normal distributions and t-distributions, they still have an area of 1 or 100%. Now, if you notice here, it looks like these curves definitely are different shapes overall, that maybe they are different sizes overall, but if a chi-square distribution really jumps up very high, then it's immediately going to have to drop down very quickly to maintain that area is still going to be 1 or 100%. Now, they are generally skewed right, which is going to be definitely different than our normal or t-distributions that were always symmetric to each other. Now, chi-square distributions are similar to a t-distribution in that they're based on degrees of freedom. And notice the more degrees of freedom that we get in a chi-square distribution, the more normal it becomes. So notice in this 10 degrees of freedom, it starts to develop a bell-shaped curve there, but it's still skewed right-ish. It's just less skewed right. The fewer the degrees of freedom you have, the more radically skewed right that it really is. Like, notice this 1 degree of freedom is like crazy skewed. Now, if you wanted to know where the mean value was, what you need to do is find your degrees of freedom. So if we had 10 degrees of freedom, then what we need to do is look at where the chi-square value is. And the x-axis here is the chi-square test statistic values. So 10 degrees of freedom means at 10 in our chi-square value here, this is roughly where we would find the mean of that chi-square distribution. And the peak is going to be at whatever the degrees of freedom minus 2 are. So notice for 10 degrees of freedom, if I subtract 2 and I went to 8 on the chi-square, the x-axis here, then that really is showing me where that distribution peaks at. Now, these aren't going to be widely used to discuss, where's the mean, where's the peak, but it gives you a good idea of how that shape is going to be formed. Now, again, we said we're going to talk about 3 chi-square tests, but specifically video 1 is going to focus on a chi-square goodness of fit, which you may abbreviate GOF test. All right, so what exactly is a chi-square goodness of test? What are we testing? Now, there's 2 different possibilities that we could be testing here. We are going to cover one of them in video 1. The other one we are going to cover in the video 1 follow-up in class. What we're going to first discuss is a distribution of varying proportions, and you have to be told what these varying proportions are. You have to be given that information in the problem, and it's of one categorical variable. What we are going to explore in video 1 are M&M color distributions. Now, the one categorical variable is M&M colors, and the different colors aren't necessarily all the same likelihood of occurring. The other thing that we're going to explore, again in the video 1 follow-up, is instead of varying proportions or unequal proportions, we could explore the idea of what if the proportions of one categorical variable are all equal to each other. So some examples would be Skittles colors are supposedly evenly distributed. That reds, orange, yellows, greens, and purples are all equally likely to occur with a 20% rate. Is birthday of the week evenly distributed? Is the proportion of people who were born on Sundays the same proportion as the people who were born on Mondays and Tuesdays and Wednesdays and Thursdays and Fridays and Saturdays? We don't know. So again, that's what we will explore in the video 1 follow-up, as if we have equal proportions. All right, so like I mentioned, not all M&M colors are equally likely to occur. Blue and oranges are supposed to happen with about a 25% rate, and greens, yellows, browns, and reds are all supposed to be equally likely at 12.5%. Now, you decide to test this delicious claim by purchasing a randomly selected bag of plain M&Ms from a grocery store. Now, one thing I didn't mention previously is that we are going to be focusing on plain M&Ms. Actually, peanut M&Ms have a different color distribution than plain M&Ms, likewise with all the other variety of M&Ms. So when we're talking about M&Ms here, we're talking about the plain old like dark brown bag. Now, without opening your randomly selected bag of M&Ms, you can feel from the outside that there's 60 M&Ms inside your bag. So the first thing we're going to explore here is how many of each color would you expect to see if the claimed distribution of 25, 25, 12.5, 12.5, 12.5, 12.5% are really correct. So if there's really 60 M&Ms, we would expect 25% of them to be blue, right? Well, how many is 25% of 60 M&Ms? So if we took 60 M&Ms and what's 25% of that, well, we would expect 15 of the M&Ms to be blue. How many M&Ms would we expect to be orange? Well, it's the same percentage, right? So we start with our total sample size. We would expect 25% of the 60, which again is another matching 15. Now, green, yellow, brown, and red. Notice that they all are 12.5%. So really, we can kind of clump these together and say out of the 60 M&Ms, we expect 12.5% of them to be green, yellow, brown, and red individually. Well, how many is that? Well, when we do the math, we get 7.5. Can we really have half of an M&M? And some of you might go, yeah, there could be a half an M&M, like it didn't, it got past quality control, and sure, I've seen half an M&M before. But the thing I want you to realize is when we talk about expected counts, it's how many we would expect to see theoretically. These aren't really going to be how many we will truly see. So if you ever get a decimal value for an expected count, and you do have to calculate these expected counts because we're going to need them to calculate what the overall chi-square test statistic is in the end of this problem. So if you get a decimal, just go ahead and, round it to 1 or 2 decimal places. There really isn't a specific number of decimal places to round to. So I would typically just do 1. If you're feeling crazy, do 2. Now, overall, how did we come up with all these expected counts? Well, we took our sample size, our N, and we multiplied it by each individual. So I'm going to do P for proportion, and then subscript individual. So we took our sample size times the proportion of blue M&Ms, 25%. We took 60 M&Ms times the proportion of orange M&Ms, 25%. Now, this kind of looks familiar, doesn't it? It's like once upon a time, we had a condition where we had to check if n times p and n times 1 minus p were both greater than or equal to 10. Boy, is that somehow related? I think it might possibly be. Now, here is what really happened when I opened up that bag of M&Ms. Now, these M&Ms here, they look more like a dark red, but it was the closest thing to brown that I could really get in there. So overall, I ended up with 11 blue M&Ms, 12 orange, 11 green, 9 yellow, 8 brown, and 9 red. And again, when I added them all up, there were the true 60 that I could feel inside the bag. Now, is what I saw happen really the same as what I expected to happen? And you can see that's not true. I saw fewer blue M&Ms than what I expected to see. I had fewer orange M&Ms than what I expected to see. I had more green M&Ms than I expected to see. I had more yellow, brown. Technically, I was at just about an even draw here, right? Like I saw 8, but I expected 7.5. But can I really expect 7.5? So you could think of 7.5 as like 7 to 8. And yeah, I saw 8. Red, I saw maybe 1-ish more than what I expected to see there. So you can see our expected counts and our observed counts, not necessarily going to be exactly the same, but could they be exactly the same? Absolutely they could be. Now, here's the thing. We really could take this M&M problem and go back to a previous chapter and do 6 hypothesis tests, 1 for each color of M&M. But do we really want to do 6 hypothesis tests when really we could do 1 hypothesis test? And I'm going to go with a bet that you guys are saying, let's do the 1 hypothesis test because I don't want to have to do 6 of them. So therefore, we are going to introduce our chi-squared goodness of fit test. It is going to do all 6 of these at once. Now, for the hypotheses, we are going back and writing hypotheses because we are testing. I have these written 2 different ways. So notice up here, I've got for varying proportions, like our M&Ms. In general, this is what the null and the alternate hypothesis is going to look like. The null hypothesis is going to be that the claimed distribution of the categorical variable, whatever we're hypothesizing about, and in this case, M&M colors, for the population of interest is correct. So the null hypothesis is we're going to assume that we are being told the truth, all right? And then for the alternate hypothesis, we want to show that what we have been told is not correct, that it really isn't 25%, 25%, 12.5, 12.5, 12.5, 12.5. Now, here's the thing. We could write our hypotheses in clear words like this. But you could, if you really, really wanted to, instead of saying this, we could say the proportion of blue M&Ms is equal to 25%, and the proportion of the orange M&Ms is equal to 25%, and the proportion of green M&Ms is equal to 12.5%. And you could write out the yellow, the brown, the red, and you could say all of these proportions are correct. Versus alternatively, at least one of these proportions is not correct. Now, notice I said there at least one proportion, because it really could be that maybe blue is spot on, that we can't really reject a blue not 25% rate, but maybe the other colors are all screwed up with each other. So when we say that they're not correct, what we're really saying is at least one of them's off, all right? Because if one of them's off, then there's a chance that maybe more of them will be off. But it doesn't mean that all of them will be off. Now, for the other situation, which is the one that we're going to cover in the video 1 follow-up in class, is what if we had equal proportions? Or what if everything was evenly distributed or uniformly distributed? So the null hypothesis would be that the categorical variable, whatever we're collecting data for the population is evenly distributed. It looks nice and even. Everything is spread out equally. Versus alternatively, that it's not evenly distributed. So again, I mentioned like birthday of the week, so the birthday of the week for all people is evenly distributed. That we have the same chances of being born on a Sunday as a Monday, as a Tuesday, as a Wednesday, Thursday, Friday, Saturday, and I started with Sunday. So versus alternatively that, Sunday may not have the same probability as Friday, may not have the same probability as Wednesday. At least one of those days is not like the others. Now, what does our hypothesis look like for our M&Ms? So again, that's more like the varying one. So we're going to say the claimed distribution of M&M colors, that's our categorical variable of interest, for all M&Ms, and again, remember, it's all plain M&Ms, is correct. So I don't have to specify what the claimed distribution is, but only if I wanted to write out, the blue is 25%. Oh, wait, I was writing 2.5%. Is 25%. And that the proportion of orange is 25%. Now, I can write all those out, or at some point, I have to be told what these numbers are, so I can just refer to them as the claimed distribution. Now, alternatively, the claimed distribution of M&M colors for all M&Ms, for all plain M&Ms, is not correct. Or again, we could say that at least one of those colors does not follow its claimed distribution. Now, conditions. Hey, guess how many there are? 3. Guess what the first one is? It's still random. And it's the same exact thing that we've been looking at before. That the sample must be stated to be either random, an SRS, or maybe it's going to use random assignment. And what were we told about our bag of M&Ms? That the bag was randomly selected. So we are good to go with the random condition. Guess what the second condition is? Yep, you guessed right, independent condition. And if random assignment is used, remember, we have no need to check the independent condition. So, in general, is the population at least 10 times our sample size? Who or what is the population? All M&Ms. Our sample size, if you remember from earlier, was 60, so 10 times that's 600. Can I assume that there are more than 600 plain M&Ms? Absolutely. Now, what's the third condition? Normal. That's what it was before when we had a normal distribution. But we're not going to call it the chi-square condition here. We have a new name for the third condition. And the third condition is just called the large counts condition. So we need a big enough something specifically, but it's not the sample size. What we need to know is, are all of the expected counts at least 5? And the chi-square distribution is going to work if all the expected counts are at least 5. Now, here's the thing. Earlier, we calculated what all of the expected counts were. And again, you have to write these out somewhere on your paper to get full credit on my test and on the AP exam. You have to list out what the expected counts are. And you can't just write out like 15, 15, 7.5, 7.5, 7.5, 7.5. You have to label what those expected counts are tied to specifically. All right. Now, the nice thing is we don't have to talk about all of these expected counts. Now, I did say are all expected counts, but if the smallest expected count is at least 5, then that must mean that all of them are at least 5, right? So the smallest expected count is really a 4-way tie for green, yellow, brown, and red. So I could state that the smallest expected count is 7.5, and therefore this condition is met. Now, what do the calculations look like? Because this is going to look completely different than what we have seen in the past, because we don't have normal CDF and TCDF to calculate a p-value for us. We're going to have something brand new. Now, this is the one and only thing that is given to you on the AP Stats exam formula sheet, and it is the formula for the chi-square statistic. So the chi-square statistic is equal to, this little funny guy is the sigma, capital sigma, which means mathematically we are going to sum up. What are we going to sum up? We are going to take a look at the observed values minus the expected values. We're going to square that difference and then divide it by the expected value. Now, here's the nice part. We already figured out what the observed counts were because, well, that was what happened when we opened up the bag of M&Ms. So we have to be given that data. The expected counts, we had to come up with those, and we mathematically determined what those expected counts were. All we have to do now is to use this formula for each color of M&M. So notice here in my work, this should look kind of familiar, this plus ... plus notation. We did this back in chapter 6 when we did binomial distributions, because sometimes we had to add up like a lot of different binomial possibilities, and we said we don't have to write out all of them. We just needed to write out the very first thing plus ... plus the very last thing that happens. So notice I've got this nicely color-coded here. So my first observed, well, blue was the first one I talked about. So I have my 11 observed blue minus my 15 expected blue, square that quantity, and then divide by the expected again. And whenever I type that into my calculator, I'm going to get a crazy decimal most of the time. So I would typically round these to 1 or 2 decimal places. Here I would probably recommend 2 decimal places more than anything. And then in terms of work, I skipped over orange, green, yellow, brown just to show you how the formula works. So The observed red, 9, minus the expected red, 7.5. Square that difference, divided by the expected 7.5. And that comes out to be an exact 0.3. Now, I also included what the other individual chi-square values are. So each of these color numbers that I get right here, we would refer to these as individual chi-square values. And what we need to do with all these little individual chi-square numbers is, capital sigma, we need to add them all up. So whenever I add up all of the chi-square individual values, then I get an overall chi-square test statistic of 3.93. So now we take that 3.93 overall chi-square test statistic and we need to convert it into a p-value. Now, previously, when we did t-test statistics, we had to take our t-test statistic and use t-CDF to turn it into a p-value. So what command are we going to use to turn a chi-square test statistic into a p-value? Well, if you look further down the list, and again, this is in the same area where we had normal CDF. We've used inverse norm. We've used inverse t. We've used t-CDF. But now we get to use chi-square CDF down here at the bottom for number 8. Now, here's what's also nice is when we first talk about, well, what is the probability that we would find other chi-square test statistics that are as extreme or more extreme than what we saw happen? And it was always kind of tricky for some people to decide, should this be a greater than or a less than sign? And it really all depended on the sign of our test statistic. But remember, one of the characteristics of a chi-square distribution I mentioned earlier is that this value is always going to be positive, which means what sign are we always going to use here is a greater than or equal to. So again, this will always be greater than or equal to whatever that chi-square value was that we calculated. And then, let me move this out of the way, then we're going to go select chi-square CDF. And our lower bound is always going to be that chi-square test statistic value that we got. The upper bound is always going to shoot up to infinity. And then we're going to need to tell the calculator how many degrees of freedom there are. So now, this is where I'm going to tell you, for a goodness of fit test, and this is going to be different for the other two types of chi-square tests that we do in video 2 and video 3, but for a goodness of fit problem, the degrees of freedom are the number of categories minus 1. Now, what are the categories in our M&M problem? The categories are the colors. So the number of colors minus 1. There were 6 colors minus 1. We have 5 degrees of freedom. So once I type in chi-square CDF with that information, I get a rather large p-value here. All right, so what does this look like with our calculator? Please tell me there is a calculator command for this. Yes, there is a calculator command. And just like previously, we have to name the procedure appropriately. We have to call it a chi-square GOF test. Can I just call it a chi-square test? No, because there's 3 different kinds of chi-square tests. So you have to be specific. This is a goodness of fit test. Now, what we need to do first is we need to go put preferably our observed counts into list 1. And we need to go type in our expected counts, preferably in list 2. All right, observed in list 1, expected in list 2. Then you can go to the same place that you went before to find all your other tests. You're just going to need to scroll down a little bit more. And here's the thing. You're going to notice that there's 2 different types of chi-square tests. There's one that's just called chi-square test. That's going to be for video 2 and video 3. What we want is option D, a chi-square GOF test. And I'll also tell you, if you have an older TI-83 Plus calculator, you are not going to see this command on your calculator. You're going to need a newer calculator. So you can borrow one of mine or get a TI-84. Now, select the chi-squared GOF test, and we need to tell it where our observed and expected data is at. By default, the observed will say list 1, the expected will say list 2. So that's why I mentioned before, it's preferable that we put our observed counts in list 1 and our expected counts in list 2, because by default, that's what the calculator is going to have them as. Our degrees of freedom, if you remember from earlier, is just our number of categories, which in this case is the number of colors minus 1. So we have 5 degrees of freedom. Now, when you go hit calculate, it's going to run the chi-squared goodness of fit test. And notice there's the same chi-squared test statistic that we got earlier. Here's the same p-value that we got earlier. And it just repeats, hey, here are the degrees of freedom. You do need to write down what the degrees of freedom are. Even though we had to tell the calculator how many degrees of freedom there were, we still need to write it down as part of our work. You would think that the calculator could look at a list and go, hey, you know what? Look, there are 6 values in this list. How about I just subtract 1 and do the math for you? But it doesn't. So write down the degrees of freedom as being 5. Now, at the bottom, you're going to see something that says CNTRB and then a squiggly bracket, and then we got 1.066666667. And if you keep hitting the right arrow key on your calculator, this will continue to scroll over and you're going to start to see other numbers happen with some spaces, a little bit of space in between them. What on earth are these numbers here? And I just want to point out, we've seen this number before, not exactly with that many decimals, but maybe, I don't know, we rounded it to 2 decimal places. So if you remember, this was the first chi-square value that we got for the blue M&Ms. When we did the observed minus the expected squared divided by expected, it was 1.07. And that's what this number really represents here. So the CNTRB, what that means is the contributions of the overall chi-square test statistic. So if you keep scrolling through this list here, you're going to see the blue chi-square value, the orange chi-square value, the green chi-square value, the yellow chi-square value, the brown chi-square value, and the red chi-square value. And it doesn't round them nicely like we did earlier, but it's those same numbers that I showed you earlier. And if we add up all of these individual contributions, we get that overall chi-square test statistic. Now, what on earth, why on earth would they even tell us about what these numbers are? Well, we can use these numbers sometimes to do a follow-up analysis, but typically only when we reject the null hypothesis. And the question that we would typically ask is, well, which thing was the most off? And in this scenario, it's which color was the most off. And all we have to do is look for the biggest value out of the entire 3.93 chi-square test statistic. So in the end, the green was the most off than what we expected to see. I'm trying to remember. I think we saw 11. We observed 11. We only expected 7.5. So there was a 3.5 difference. But remember, it's not just the difference as being the highest contributor, but it was really the square difference divided by what we thought should happen. So that is that 1.63 value. All right, so now in the end, we finally get to the conclusion. The p-value is 0.5595, which is clearly nowhere near being less than an alpha level of 5%. So therefore, we are going to fail to reject the null hypothesis. So in the end, since we failed to reject, we get to say that we do not have enough evidence at an alpha 5 point of 5% to conclude that the claimed distribution of M&M colors for all M&Ms is not correct. Now, this sounds like we're saying a double negative here, right? We do not have enough evidence to say that it's not correct. So aren't we really saying that it is correct? Not really, because remember, we're always trying to conclude the alternate hypothesis. Do we have enough evidence to conclude that it's really not right? No, we do not have enough evidence that it's really not right. But that doesn't mean that it's technically true. There still is the possibility that maybe we made the wrong decision. Like, I don't know, a type 2 error. So again, remember, the alternate is the thing that we're always trying to conclude. Now, the you-do problem. What I want you to do is I gave you a new bag of M&Ms. You didn't even see it, but I gave you a new bag. Oh, I'm sorry. I ate the M&Ms. I'm just reporting what I ate. And these are still the same expected values here. All right. So we're still using the 25%, 25%, 12.5% for the other 4 colors. What I want you to do is to calculate the overall chi-square test statistic using that formula that I shared with you. And then I want you to convert that test statistic into a p-value. And I want you to do it by hand. I do not want you to go use that chi-squared GOF test that's in your calculator. You're going to get lots of practice with using that thing. Now you might go, why would I need to figure out what the p-value is by hand? I don't know, that sounds like it would be an awfully good multiple choice question to throw on a test, don't you think? All right, good luck with that, and we will talk about these the next day in class.